Hello everyone, my name is Christopher Wheatley, and welcome to my final presentation with the Texas A&M O-REU program. My research this summer has been over self-interstitial defects in copper. This research seeks to better understand how these tiny phenomena behave on an atomistic level and use that knowledge to develop metallic alloys that are more resistant to irradiated environments. Radiation is an extreme environment to both humans and the materials we use to control it. Nuclear fusion and fission reactions release neutrons with velocities similar to that of a particle accelerator, and these neutrons act as a bombardment on the materials that enclose the nuclear reaction, as you can see in the simulation by one of my fellow RU students. These collisions create many defects, and it is these defects that I am interested in. The defects I'm interested in with this research are self-interstitial atoms, or SIAs in copper, where one copper atom has been inserted into the lattice, resulting in two atoms where there should only be space for one. There are 6 such interstitial structures in FCC metals like copper, as you can see on the left, but only one is the most stable, the 100 dumbbell interstitial. I am seeking to accurately simulate these defects and their interactions in the crystal lattice, as you can see on the bottom right. It should be possible that through deforming the copper, the energies of all of these interstitials will shift, leading to one of them dethroning the 100 dumbbell and becoming a new, most stable interstitial. To find a new stable interstitial, I need to know how to deform the copper. To find this, I calculated p-tensors, which measure the first moment of the force distribution. We can use them to find how the defect interacts with the crystal's strain field. Looking at the p-tensors, there are 2 strong candidates, the 110 dumbbell and the Crowdion interstitial. These both have values that are close to the 100 dumbbell, but even more importantly, they have off-diagonal sections. What these off-diagonal sections mean is that by applying a shear strain in the xy direction, which the strain tensor represents, it can change the energy of these two without drastically changing the 100 dumbbell as well. All that is needed is to provide enough strain, and the most energetically stable configuration can change. So knowing this, for my testing I used lamps to apply the strain and output the energy of the structure, as you will see in plots, and then using O-REU to visualize the atomic models. Both of these plots, as well as the actual simulations that you can visualize, should support one another, and energy changes should result in visual changes as well. This graph shows the predicted values of the interstitials as straight lines and the actual data in markers. The equation on the right shows how the theorized energy changes was calculated, including both of the p-tensors, as you can see in here, as well as the calculated strain, as you can see here in Einstein notation. As can be seen by the graph, there is a discrepancy as the strain increases, which should be due to structure changes in our atomistic simulation. Looking at this graph of the actual results by themselves, there are 2 substantial energy shifts seen. First, around 2 to 3%, the 100 dumbbell drops to follow the 110 dumbbell's path. Secondly, around 7% strain, the Crowdion seemingly continues a parabolic relationship that we originally see with the 100. What I mean by that is if you connect this dot to this dot, it seems to have one smooth curve going from one to the other. Starting out by looking at the 100 dumbbell, it begins in its horizontal position, but later, as strain increases, it shifts into the diagonal position of the 110. And as we can see in the graph by itself, that is the same energy shift we see in the 2 to 3% range. Here you can see the Crowdion shift into the 100 dumbbell position at around 7% strain. You can see this in both the graph and the simulation supporting each other. The 110 dumbbell does not change throughout the simulation, which supports the hypothesis that this structure has the lowest energy under applied strain. In addition, during the entire graph, there is no sharp transition but a simple linear plot. What these plots have shown us is that it is possible to induce a new stable interstitial through deformation. The question was then asked, what happens when a strain is applied in the opposite direction, meaning in the negative xy? Looking at the three interstitials, both the 100 dumbbell and the Crowdion have symmetry across the x and y planes. The 110 dumbbell, however, does not. And so when the energies were calculated in either direction, while the two symmetric interstitials mirrored, there was an odd increase on the 110. Looking at the animation, the 110 originally resists the strain, which is why there is a continued linear increase on the formation graph. Eventually, however, the strain is too much, and the 110 switches to a 1 bar 10, which is the same defect, just in a different orientation. Beyond this jump, the two linear sections are equivalent, suggesting that while there is a change in orientation, the 110 dumbbell and its family is the most stable. So we've examined the energies and found that yes, the energy structure does change with strain. But does that mean how the defect migrates through the lattice changes as well? Here you can see a molecular dynamics simulation of the 100 dumbbell. First, a 2% strain is applied, and then the defect is kept at a constant 300 Kelvin to see how the defect migrates. 2% appears to be the transition point, as the defect keeps swapping between different orientations of the 100 dumbbell. But what if we move past the transition point? Here we have the same simulation, except the strain has been increased to 3 and 4% respectively. It has been shown that the interstitial should transition to the diagonal 110 dumbbell, but not if the migration also changes. As we start the simulation, we can see that this time the migration pattern is completely different in the 110 direction. This has been the goal of my research this summer, to find these migration patterns, and it is exciting to show that they actually exist. These interactions expand what we know about these defects, and in turn we can use this knowledge to build better materials. As I close this talk, I want to leave with two main points: that a strain can induce stable interstitial structures, and that these stable interstitials migrate in vastly different ways, as we have seen with the 110 dumbbell becoming more stable than the 100 dumbbell. However, there is still much to uncover. We still need to answer what the energies of transition are, which could be solved with the nudged elastic band method, as well as test additional interstitials and strains to determine if the 110 is truly the most stable with applied strain. My biggest goal this summer has been to study the interaction of these defects. Controlling the energy and migration can provide radiation-resistant or self-healing metals very much needed in these extreme environments, and it has been fascinating to study them. Finally, I want to give a big thanks to all the supporters of my research this summer. I could not have done this without the expertise and support of Dr. Peng Chen and Professor Michael Dimkovich. And thank you to the members of the Dimkovich Research Group for your help in preparing my presentations. And thank you to Texas A&M, the CREDS Group, the National Science Foundation, and the National Nuclear Safety Administration for making this program and my research a possibility. It's been a pleasure working on this project, and I look forward to seeing where this research goes. Thank you.